In this video we're going to look at angular projection. Suppose we have a particle that is projected at an angle of theta above the horizontal with a velocity of u. The horizontal velocity, so what we've got then is we'll have to resolve u to the horizontal, and the resultant or the component of a force or of anything is its magnitude multiplied by the cosine of the angle. So the horizontal is going to be u cos theta. The vertical component then is going to be u sine theta. Or if you like to keep things in terms of cos, it would be u cos 90 minus theta. And the vertical velocity will be reduced by the gravitational constant g. So we know g is always acting down the way. So if something has been thrown up or projected up in the air, whenever gravity is being applied, it'll be pulling it down towards the Earth. So on the path on the way up, the velocity will be decreasing, the vertical velocity that is, and then on the way back down again, the vertical velocity will be increasing. The trajectory is symmetrical. The flight time is twice the time taken for the particle to reach the highest point. So because the constant due to gravity is well, it's constant, I suppose. The velocity then is going to decrease up to zero, and then it will increase at the same rate that it had been decreasing because the force is gravity. So the time that it takes to slow down will be the same time that it takes to speed up. So the flight time can be calculated by doubling the time taken to reach the highest point. And when we reach the highest point, remember that the upwards velocity is going to be zero. There'll still be a horizontal velocity, and it'll still be the same of u cos theta. The direction of motion at any other time is found by considering the horizontal and vertical components. So no matter where we are, we would pick the point, we'd find the horizontal and the vertical component, and then resolve that. And that's going to be the same anywhere along it. Obviously, if you're on the rise, then the vertical component will be up the way, or upwards. During the first half of motion, the particle is travelling at an angle above the horizontal, and in the second half it's below the horizontal. And hopefully we can see that it's definitely below, because the angle, the resultant and the horizontal, well, the resultant's beneath it. So hopefully that's obvious. So example, a particle is projected from a point on a horizontal plane and an initial velocity of 28√3 meters per second at an angle of elevation of 60 degrees. So if we mark in our point, it's projected upwards with a 60-degree angle, and we'll come back down again. So we could mark in our horizontal, and we can also mark in the angle of 60 degrees that it's been projected with. And we know that the velocity at that projection was 28√3 meters per second. So find the greatest height of the particle and then the time taken to reach this point. So what we've got, we need to look at the components of this velocity, and the horizontal component is going to be 28√3 cos 60, and the vertical component is 28√3 sine 60. So if we look at the vertical motion and consider suvat, we are looking at maximum height. The initial velocity in the vertical plane, we're taking up as positive, will be 28√3 sine 60. Final velocity at the maximum height is going to be 0. The acceleration is minus 9.8, and we are also trying to work out the time, so we can do that as a secondary issue. So S, U, V and A, we've got the equation v squared equals u squared plus 2as. V squared is 0 squared. U, which is 28 root 3 sine 60 squared plus 2 times minus 9.8 times s. What we have then is 19.6s equals 1764. So then dividing by 19.6, we get s to be 90 meters. Then we need to work out the height, the time taken to reach this point. So we can apply v equals u plus at, and 0, the final velocity, is the initial velocity, so 28 root 3 sine 60 plus minus 9.8t. So 9.8t equals 42. So t then is going to be 4 2/7 seconds. Next example then, a particle is projected from a point on a horizontal plane and has an initial velocity of 45 meters per second at an angle of elevation of the inverse tan of 3/4. Find the time of the flight and the range of the particle of the horizontal plane. Now, range is just the horizontal distance travelled. So I've drawn a diagram here. The black is the projection. We've got 45 meters per second, an angle of theta. Now we'll work out that in a minute or two. The horizontal component then is 45 cos theta, and the vertical is 45 sine theta. Now this, whenever it's given us that the angle of elevation, so theta is tan to the minus 1 of 3/4, that means that the opposite and the adjacent lengths would be 3 and 4. And if we use Pythagoras' theorem, then that means that the hypotenuse would equal 5. So from there we know that the sine of theta, which is the opposite over the hypotenuse, that's going to be 3/5, and the cos of theta, which is the adjacent over the hypotenuse, is going to be 4/5. So the horizontal component is 45 cos theta. Cos theta is 4/5, so 4/5 times 45 is going to be 36, and 3/5 for the sine of theta, 3/5 of 45 is going to be 27. So those are the vertical and horizontal components then of the velocity. Now we're asked for the time of flight. So what we need to do there is look at the particle vertically and find the time taken for it to reach the maximum height. And the time taken to get up is going to be the time taken to get down again. So if we work the time up, we can double our answer to get there. So the time taken to get to the maximum height, if we do our SUVAT information, so the final velocity is going to be 0. The initial velocity is 27. The height we're not looking for, so we don't care about that. The acceleration, well, it's gravity, and gravity is acting down the way. Obviously in this we've taken vertically as positive, so that means acceleration is going to be minus 9.8, and time is what we're interested in. So we've got u, v, a and t. Our equation is going to be v equals u plus at. So v is 0, u is 27, plus minus 9.8t. So 9.8t must equal 27. So that means that t equals 2.755. But that's just for the time up. So therefore the total time, if we double that, is 5.51 seconds to 3 significant figures. Now we're asked to find the range. So what we have to do is think about the horizontal motion, and that's using the formula S equals Vt. So we know S is what we're looking for. The velocity is 36, the horizontal component was 36, and the time was 5.51. So if we multiply our answer by 36, we get the range is 198.367. So that's 198 meters to 3 significant figures. Next example then, a particle is projected from an origin O with a velocity of 30I plus 40J. What that means is the horizontal component is 30I and the vertical component is 40J. Find the position and velocity 5 seconds later, and hence find the distance of the particle from O and the speed and the direction of its motion. And this time we're taking G as 10. So the first thing we're trying to do is find the position, so find where it is, and the velocity vectors after 5 seconds. So if we go horizontally, we know that S equals VT. Now these are vectors now, so we're going to underline S and V. The S is going to be 30I times 5, which is 150I. Vertically, we get S, U, V, A, and T. A, V, U, and S are all vectors. Time is 5 again. The S is what we're interested in. Initial velocity was 40J. The final velocity we don't know. The acceleration is minus 10J. So we can keep it in J form. So we know it's 10 meters per second down, or 10 meters per squared second down the way, and because it's a vertical motion then it's going to be J. So it would be minus 10 then. So our equation then is going to be S equals UT plus a half AT squared. So the initial velocity was 40 J times 5 plus a half of minus 10 J times 5 squared, which is 200J minus 125J, which is going to be 75J. So the position of the vector after 5 seconds is 150I plus 75J meters. Now we also want to work out the velocity after 5 seconds. So horizontally, the velocity always is the same, so it's going to be 30I. Vertically, again we can do our constant acceleration. So S we kind of know, but we're best trying to avoid it if we can. The initial velocity is 40J. Final velocity is what we're interested in. The acceleration is minus 10J, and the time taken is 5. So our equation there is V equals U plus AT. And I'm avoiding using 75J as the distance, just in case I've made a mistake in that. So the velocity is going to be 40J plus minus 10J times 5, which gives us a velocity of minus 10J. So the velocity after 5 seconds is 30I minus 10J meters per second. So now what we're looking to do is find the distance travelled from the particle. So the distance is the magnitude of the displacement. Which is going to be the magnitude of 150I plus 75J, which is the square root of 150 squared plus 75 squared, which is 167.7 meters. Then we're going to try and find the speed. and again the speed is the magnitude of the velocity, which is the magnitude of 30I minus 10J, which is the square root of 30 squared plus minus 10 squared, which is 31.6 meters per second. And the final thing we were asked for was the direction of its motion at this time. So what we know, at t equals 5, the velocity is 30I to the right and then 10J down the way. So if we're trying to work out the angle that it's working at, it's the angle beneath the horizontal. So tan theta is opposite over adjacent, so that's 10 over 30. So theta then is tan to the minus 1 of 10 over 30, which is 18.4 degrees. So where the particle is travelling at 31.6 meters per second, 18.4 degrees below the horizontal. Example, a stone is thrown from the edge of a vertical cliff with a velocity of 50, an angle of 7 over 24 above the horizontal. Now, again, if we have that theta is tan to the minus 1 of 7 over 24, that means that the opposite and the adjacent are 7 and 24 respectively. So that means the hypotenuse is going to be 25. So from that we know that the sine of theta is going to be 7 over 25 and the cos of theta is going to be 24 over 25. The stone strikes the sea at a point 240 metres from the foot of the cliff. Find the time for which the stone is in the air and the height of the cliff. So let's draw a wee picture then to try and see what's going on here. So we've got the sea level marked down below. We've got the height of the cliff and then the point of projection, which was thrown at 50 metres per second at an angle of theta to the horizontal, and the path will follow this parabola. Now we know the distance travelled from the base of the cliff to the point where the stone hit the sea is 240 metres, and then we've got all this information about theta. So if we use the range of 240 metres, we can look horizontally and use S equals Vt to work out the time that it's in the air. So the horizontal direction was 240 metres, the velocity was 50 cos theta times t. So 240 divided by 50 cos theta, and we know that cos theta is 24 over 25. So that's going to equal t, which is 5. So t is 5 seconds. To find the height of the cliff, so we can do the vertical direction. And if we do suvat, S is what we're interested in. U is going to be minus 50 sine theta. So what we're doing is we're going to take down as positive, and we're just looking for h. We don't need to work out how or the maximum height and then the time taken to go down or anything like that. Because these are all vector forms, we can take h is what we're trying to find, and if we take this as our 0 level, then the velocity up is a negative, and that's going to help us. So the final velocity we don't care about. The acceleration is going to be positive 9.8 because we're taken down as positive, and we know the time taken is 5. So with this we're going to use S equals ut plus a half at squared. So S then is going to equal minus 50 sine theta times time, which is 5, plus a half of 9.8 times 5 squared. We know the sine of theta is 7 over 25, so we can substitute that in, and we get a height of, so that's 52.5 meters. A shell is fired from a gun, has a horizontal range of 960 meters and a flight time of 12 seconds. Find the magnitude and direction of the velocity of the projection, taking g as 10. So we've shown the projection of the shell. We know the horizontal distance is 960 meters and t equals 12, and we're taking gravity typed down away at 10 meters per squared second. Now, whenever we have the horizontal distance, we know that, so horizontally, S equals Vt. So 960 is going to equal the horizontal component of the velocity times t, which is 12. So dividing by 12, we get that V equals 80 meters per second. Vertically, if we do our suvat, we could set this up that the vertical displacement is 0. The initial velocity is what we're interested in. The final velocity we don't know. The acceleration is minus 10, so we're going to take up as positive. And then the time taken is 12. So then we've got S equals ut plus a half at squared. So 0 equals 12u minus 5t squared, which is 5 times 12 squared. So 720 equals 12u, so then u equals 60 meters per second. So we've got a vertical velocity of 60 and a horizontal velocity of 80. So to work out the magnitude and direction of the velocity, the magnitude of the velocity is going to be 60 squared plus 80 squared, square rooted, which gives us a magnitude of 100 meters per second. Then we need to work out the angle through which it's been projected. So we've got 80 horizontally, 60 vertically. The angle is between those. We can use tan. So tan theta equals 60 over 80. So then theta is going to be 36.9 degrees. So the shell was fired with a velocity of 100 meters per second at an angle of 36.9 degrees to the horizontal. In our next example, a ball is projected with a velocity of 28 meters per second. If the range of the ball is 64, find the two possible angles of projection. So what we've got then is the horizontal range. We know that the velocity has been projected at 28, and it could either be a low angle or a higher angle for us to get the two different angles. But if we let them equal theta degrees, then we've got the horizontal component is going to be 28 cos theta, and the vertical component is 28 sine theta. So let's look at the information that we have for each. If we look horizontally, we know that S equals Vt. So S of 64 meters is going to equal 28 cos theta times t. And divide by 28, we would get that 16 over 7 is equal to cos theta t. Then we can look vertically. And look at our suvat information. S could be 0. The initial velocity is 28 sine theta. The velocity at which it'll hit the ground will be minus 28 sine theta, and that's taken up as positive. The acceleration is minus 9.8, and the time taken is t. So if we use v equals u plus at, we'll get that minus 28 sine theta equals 28 sine theta minus 9.8t. So 9.8t then is going to be 56 sine theta. What we can do as well in the horizontal then, we could rearrange for t, and you would get t equals 16 over 7 cos theta. And we can substitute that in for t into the vertical one, and we get 9.8 times 16 over 7 cos theta equals 56 sine theta. So that's 22.4 over cos theta equals 56 sine theta. 22.4 then is going to equal 56 sine theta cos theta. And I'm going to divide through by 28, and I get 0.8 equals 2 sine theta cos theta. Now I've been very specific in dividing by 28 because I want to get 2 sine theta cos theta, because what I know about 2 sine theta cos theta using the double angle formula, the sine of 2 theta. So sine 2 theta equals 0.8. The basic angle is going to be the inverse sine of 0.8, which works out to be 53.1 degrees. So I can go to my cast diagram. It's positive within A and S. So that means that 2 theta could be 53.1 degrees or 126.9 degrees. Divided by 2 then, theta could be 26.6 degrees or 63.5 degrees to 3 significant figures. And then the last example, a golfer hits the ball with a velocity of 52, an angle of alpha above the horizontal where tan alpha is 5 over 12. That tells us that the opposite over the adjacent is 5 over 12, and using Pythagoras' theorem we can find that the hypotenuse equals 13. So sine alpha is going to be 5 over 13, and cos alpha is going to be 12 over 13. So set up a mathematical model of this situation and determine the time for which the ball is at least 15 metres above the ground, and take g as 10 metres per squared second. That's down the way. Now this is a common addition to these questions, so we must consider the assumptions that we need to make whenever we're answering this question. And our modelling assumptions are the following. So we should consider the golf ball as a particle. That means we're going to have a negligible size, so we can ignore air resistance and things like that. We also assume that any air resistance is negligible. We assume the ground to be level, and we assume that nothing impedes the motion of the ball and that the motion occurs in one vertical plane. So those assumptions make it much easier to solve. So if we consider the golf shot, let's draw a picture of this. We've got our horizontal, and the ball will be projected up in the air and then come back down again. And what we're looking to do is try and find the time for which the ball is greater than 15 metres above the ground. Okay. So the other things then we should add on, we know that the velocity is 52 and the angle is alpha. To the horizontal it's going to be 52 cos alpha, and to the vertical it's 52 sine alpha. So if we look at the vertical components and look at SUVAT, the vertical distance is 15. The initial velocity is 52 sine alpha, which is 52 times 5 over 13, which is 20. The final velocity we don't know about. The acceleration is minus 10 because we're taken up to be positive, and then the time taken is what we're looking for. So we can apply S equals ut plus a half at squared. 15 equals 20t. A half of minus 10 is minus 5t squared. So we've got 5t squared minus 20t plus 15 is 0. Dividing by 5, we get t squared minus 4t plus 3 equals 0. We can factorise that to give t minus 3 and t minus 1 equals 0. So we get t equals 3 and t equals 1. In other words, the first time that it reaches 15 metres will be at 1 second, and then on its way down, that's t equals 3. So we're asked for the time for which it was at least 15 metres above the ground, so it was 2 seconds is the answer then, that it was above the ground, or above 15 metres.